Thank you very much for the nice introduction. So Mauricio already did an amazing introduction to why explainable AI is needed, and explain some of the things we can extract from there. And he mostly focused on the most common type of explainability, which is in the form of heat maps or saliency maps. And what I want to talk about today is basically provide a bit of an overview of two other types of explainability, namely example-based and concept-based. I'm having some issues apparently. Oh, okay. Yeah, I know why.
It's good. It's good.
Yeah, I started from the end of the presentation. Okay, so basically, like in terms of explainable AI, as I initially said, so Mauricio mostly talked about like these visual explanations that can be computed like in like two different ways, either like by through backpropagation or through perturbation-based methods. But there are like many other types of explainable AI that could be used for medical images or in general, and one of which being example-based explanations, but also like concept-based explanations and textual explanations that can be like in the form of image captioning or something a bit more sophisticated. And that is something that Isabel will talk about later. So yeah, for saliency maps, basically this consists on highlighting pixels in the image that contribute to the model decision. And this could be like pixels that are actually related to pathology, or it could be like shortcuts, as Mauricio previously showed. But we have other types, and one type that is extremely interesting, especially in the case of radiology, is example-based or case-based explanations. And this is a very simple type of explanation where we just present past cases that help us justify a model's prediction. And as I said, like in radiology, this is one of the preferred ways of explaining because it aligns with medical practice. So like radiologists already looked for similar cases, even when they are not using AI systems. And in this type of explanations, we can think of like two different subtypes. So we can provide explanations based on real data, meaning based on images that were acquired from real patients. And we can also have counterfactual explanations where here we use AI to generate synthetic images that allow us to understand the what-if scenarios. So if something was different, how would this image look like? And this also helps us explain model decisions. And if we are just like looking into explanations based on real data, here there are basically two ways of extracting these explanations. So one would be by using what we call as intrinsically interpretable models, meaning that the decision process of the model would be case-based. So like the decision would be based on like different real cases. Or it can be in a post hoc manner, as for instance, like the saliency map methods that were presented before, where we train our model to solve a task. And then after we have this model deployed, we want to understand what were the causes of this decision. And if it's like in model or if it's intrinsically interpretable, so here we use like the training images in the reasoning process to make a decision about a specific case we are analyzing right now. And this can be done in like two ways as well. So it can be like distance-based in the sense that we are like comparing the current case to other images, and like by measuring this similarity, we make the decisions, and then it's very easy to extract the explanations. But it can also be more like refined, and instead of comparing similarity in between images, we can compare similarity between parts of the image, and that is what is called as prototype-based. And as I said, the other way of explaining is we have a model. So in the sense, like this model is learned without having any case-based reasoning in mind. So it's just like a classic AI model approach where we'll classify the images based on the latent representation that we learn and about on this semantic representation. And then what we do is we use like real cases, past cases, and we try to find the closest training samples, not in terms of overall similarity, but in terms of similarity related to the task. And then we measure this similarity in a semantic space that is associated to the task we are trying to solve. And by retrieving the most similar cases to the current one, we also can explain these models. And this is like an overview of example-based explanations. Okay, but like the thing with example-based explanations, or even like with saliency maps, is like, so we have a visual explanation. But sometimes it's difficult to understand the decisions of the models because, okay, we know which regions of the image were highlighted, or we know which images are similar, but we don't know why. And it can still be very difficult to understand the decisions. And because of that, there is like a completely different type of explanations that is called concept-based explainable AI. And here what we do is we try to explain the AI decisions, not by having visual explanations, but by associating the model predictions with semantic concepts. In the case of like healthcare would be to like clinical concepts. And here there are like two main approaches that can be described by these two papers. And the first one being TCAVs, or quantitative testing with concept activation vectors. And here the idea, and I have a non-medical example, but this is also done in the medical setting, and it's something that we are also exploring even for like generalizability purposes. So the idea here is we have a model, and this model was already trained, is already being used, and now we want to understand if a specific concept is relevant for this model. For instance, in the case I have in the slide, the idea was to try to understand if stripes was a concept that is relevant to classify zebras. So what we have is like we have deep learning model that was already trained. And what we need in order to understand if this concept is relevant to classify zebras is we need to collect sets of examples where we have this concept and where we don't have this concept. And then we will, basically what we do is we pass both sets of images through the deep learning network that we already had. And we look into a semantic space, and then we try to see if we can differentiate, if we can learn like a linear classifier that distinguish these two sets of representations. And based on this linear classifier, we know, or we identify the direction of the concept that then will be used to understand if this is a relevant concept or not. Another type of approach, but with the same goal, is what was called as a concept bottleneck model. So here, what we do is we directly predict some concepts that we know are relevant for a specific task. And we want to predict them based on the image. And then the final decision will be based on the concepts. So we use these concepts to make the final prediction. And by doing so, we already know like which concepts can be relevant or not. And more than that, if the learning of these concepts is incorrect, because we have this bottleneck of concepts, we can intervene and correct some concept predictions so that we avoid some misclassifications. And that is everything that I wanted to talk about. So basically, just like as a summary, as Mauricio presented, and what is very common is to have these visual explanations in the form of saliency maps that allow us to identify regions of the image that are relevant. But that is not the only type of explaining AI. And we can also do it based on examples from past cases or counterfactual synthetic images. But also we can use concepts that we know are relevant. to try to explain. And this can be, as I mentioned, well, with these zebras and the stripes, but you can think about the same in breast cancer, for instance, like connecting with BI-RADS. And that's exactly what we are exploring right now in my group. And we are even trying to do this as a regularization step, so to improve the generalizability of the models. And yeah, that's it. So thank you very much.